Hello everyone, welcome to VNR VJIT Digital Classroom Board. I, Dr. V. Pradeep Kumar, working as Assistant Professor in the EC department. Today we'll go to start about a session called Hamming Code Error Detection and Correction Method. This topic comes for second year first semester ECE students in the course Digital Logic Design. So let's start with our session. Our session is Hamming Code. It's for second year's first semester. What is an error code? Hamming error code and correction. It's a method where when we are transmitting any bits of data from a transmitter to receiver, then while transmitting due to noise, EMF, we'll get some bits error. So to overcome that bit error and to correct it, we'll use different methods. It can be a single bit error method, or it can be a multiple bit error method, or it can be a burst method. What is single bit error? If only one bit, if you are transmitting 8 bits, in that if you are getting disturbed with one bit, then it's called a single bit error. If multiple gets are swapped, then it's called as a multiple bit error. Similar way, if we have a consecutive bits get swapped, then it's called as a burst error. So Hamming method is the method which is used for error detecting and correcting for single bit method. We have a parity bit also. This we are two types. One is even parity and odd parity method. So for this Hamming code method, we need to consider parity bits also. So these are the different error detecting methods, that is parity check method, checksum method, cyclic redundancy check method, and Hamming code method. Parity method, it can detect the error, but it cannot correct it. Checksum is also same, it detects the error, but it cannot correct the error. CRC, it is also one type of an error detecting method, but not for correcting. Hamming code is the only method where we can detect it and we can correct it, but it's a single bit method. So as I said, Hamming code is a number of bits getting deferred in the two binary strings, which was developed by Richard Hamming, and hence it's the name called as Hamming code. And the purpose of this Hamming code is to detect the single bit errors and to correct that single bit error. Advantages of Hamming code are it's fast, simple hardware designing, widely used in the memory systems because we can even correct the errors. It is used for ECC RAM memory and also in the communication system. Here I will show an example. See, the data what we are transmitting is 101101, which is of 8 bits. If one bit get changed, like see in the second one, it is 141001. So one bit got changed in the position of 3. So if one bit is getting changed at the receiver side, then we'll use the method called as Hamming detecting method. I will explain you now the procedure for this data formation, error finding, and error correcting. We'll go one by one. So first, why do we add in parity bits? As I said, parity bits are of two types, even parity and odd parity. And this is added to the Hamming code to enable the receiver to detect and locate the error in the transmitted data. When we are transmitting any data from a transmitter to a receiver, along with the data, we will add the parity bits. And that parity bits helps to detect and locate the errors based on even parity and odd parity. And how do you find the number of parity bits to be added for the data? That is given by the formula 2 power r greater than or equal to m plus r plus 1, where r indicates for parity bits and m indicates for data bits. See, for example, the data bits are of 4. It means I can take an example of 1101. This is the data bits. We have 4 bits of data. Now, how many parity bits to be added to this? That is given by the formula 2 power r greater than or equal to m plus r plus 1. So let's try for different values of r. If r is equals to 1, then what is the formula? 2 power 1 greater than or equal to, what is m value? Here it's a 4 bits. So 4 plus, what is the r value? It is 1 plus 1. So it is 2 greater than or equal to 6, which is wrong. So r should not be equal to 1. Likewise, we'll try with second one. If r is equals to 2, then it is 2 power 2, data bits are 4, r bits are 2 plus 1. So 2 power 2 is how much? It's again 4. 4 greater than or equal to 7. So this condition also fails. So r value 2 is also not correct. Then we'll go for the third one. Let r is equals to 3. If r is equals to 3, then 2 power 3 greater than or equal to 4 plus 3 plus 1. How much it is now? 2 power 3 is 8 greater than or equal to 8. So the condition satisfies. 8 is equals to 8. Hence r equal to 3 is the number of parity bits we are supposed to add with the data bits 101101, 4 bits. So totally how many bits it becomes now? 7 bits. And the frame for this is shown here. That is first position to 7th position, LSB to MSB bit. Now we identified the number of parity bits. Parity bits are equals to 3 and data bits are equals to 4, totally 7 bits. Now we need to find the position. The parity bit positions are given by power of 2. That is this. The parity bit occupies power of 2. So power of 2 means 2 power 0, 2 power 1, 2 power 2, 2 power 3 and so on like this. So we need only 3 parity bits. So we need to consider only first 3. So 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4. So the position for parity bits is P1, P2, P4 out of total 7 bits. That's the reason in the first it starts with LSB, P1, P2, D1, it's a data bit because the parity bit position is P4. So this is your P4, P1, P2, P4 and the remaining bits are your data bits, that is D1, D2, D3, D4. Starts with LSB. This is D1, D2, D3, D4. This is how you will frame the verb. So what we understood in this slide, what is the formula to find out the number of parity bits which to be added to the Hamming data bits to pass to the receiver, and how to place that parity bits by using the power of 2. Clear? Now we will see with an example. See, here is the data 1011. This is the data bit, or this is the data which is being supposed to be transmitted to the receiver, to which I need to add parity bits. So the position says P1, P2. Third position is 1. It starts with here LSB to MSB. So 1011. This is your D1, D2, D3 and D4. So 1101. And the parity bits. Now need to find the values of parity bits. That is P1, P2, P4. So how do you find the parity bits? For finding the P1 from the given data frame, it starts with parity 1. So 1 replace with the same. When you're finding for the P1, it started with 1. So start the sequence with 1. Leave one number, write the next number 3. Leave one number 5. Leave one number 7. Leave one number 9, so on like this. Now to find out P2 value, it starts with P2. So that's the reason start the number with 2. It is 2. So take two digits at a time. So 2, 3. Leave 2 digits. 2, 3. Leave 2. 4 and 5 should be leaved. Then you will get 6 and 7. Again leave 2 more numbers. 8, 9 should be leave. 10, 11. These are the positions. Similar way, the next one is P4. So it started with 4. So that's the reason 4 numbers at a time. 4, 5, 6, 7. Leave 4 numbers. 8, 9, 10, 11 should be leave, and then start with 12, 13, 14, 15 like this. So this is how you need to find. Repeating again, to find the values of parities P1, P2 and P4, the formula is like for P1 finding it, it is P1, so 1 bit, and should starts with 1. So 1 bit, first position, leave 1 word, third position, leave 1 position, 5, leave 1 position, 7, leave 1 position, 9. This is how the sequence. Similar way for P2, it started with 2, so that's the reason 2 numbers at a time we have to take. 2, 3, leave 2 bits, 4 and 5 should be leave, 6, 7, leave 2 bits, 8, 9, 10, 11. Similar way for P4. Now for example, if I want to find for P8, because the parity bits are nothing but what? Power of 2. So we have 2 power 0, 2 power 1, 2 power 2, 2 power 4. 2 power 0 is 1, that is nothing but P1. 2 power 1, 2 P2. 2 power 2, 4 P4. Next, sorry, 2 power 3, it is P8. So if I want to find the value of P8, then 8 bits at a time you have to take, and it should start with number 8, 8th position. So 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8. Leave 8 numbers and then start the next sequence. This is how the value of P1 parity bits are being identified. See here the example for P1 to check. The values are 1, 3, 5, 7. For P2, it is 2, 3. Leave 2 numbers, 6, 7. For P4, 4, 5, 6, 7. Therefore, the parity bit positions are. Now for the same data bits, here P1, how do you find the value of P1 now? What is the value of P1? It's 1, 3, 5, 7. So see the data frame. From this data frame, what is P1? First position, it is same P1. Third position, we have 1. And in the 5th position, here we have 1. And in the 7th position also we have 1. So we are sending this data transmit by using even parity. What is even parity now? The number of ones should be even. What is odd parity? The number of ones should be odd. So using even parity, when I'm transmitting the data, then the number of ones should be even. But I have how many ones? 1, 2, 3. It's an odd number. So what makes the P1 such that it becomes an even number? If it is 1, then the total number of ones are even number. Got it? And that's the reason P1 value is 1. This is. For example, if I have third position as 0, then need to find the value of P1 using even parity. Then see, what will the value of P1 now? I have 2 ones. So already 2 is nothing but an even number. So P1 should be now a 0. Then only the number of ones are even. That is how we need to find out the value of P1. Similar way, we'll find the value for P2. What is P2 sequence? It starts with 2 digits 2, 3, 6, 7. Ours is 7-bit, so the maximum number should be only up to 7. Now what is the position in the second position? It's P2. And in the third position, we have 1. In the 6th position, we have 0. And in the 7th position, we have again 1. Now using even parity, count the number of ones. We have 2. So it's an even number. So what should be the P2 value? P2 value should be 0. Hence P2 is equals to 0. If I make P2 equals to 1, then it becomes 1, 2, 3, odd number. But we are transmitting using even parity. So your P2 value should be 0. That is this, the position of P2. Similar way, finding for P4. P4, how the sequence started? It starts with 4, 5, 6, 7. The maximum number of bits are 7. So the maximum number is 7. Now find the position values. P4, we have only P4 in the 4th position. In the 5th position, we have 1, 1. In the 6th position, we have 0. And in the 7th position, we have again 1. So number of ones are again here, even number. So P4 value should be 0. So that is this. Now what is the data frame completely? Your 7th win. This is your D4 value, D3 value, D2 value, D1 value. The data bits what they have given plus the parity bits. P4 value is 0, 0. P2 value is 0, 0. And P1 value was 1. So this is how you will frame a bits for transmitting to the receiver. I hope it's clear now. So now this is how the data frame is prepared. Now how to detect an error? We have transmitted the bits from a transmitter to the receiver. Now if any bit is getting swapped or getting changed while because of noise or EMF or some other reasons, if the signal is getting or if the bit is getting errored, then how do you detect it and how do you correct it? We'll go with an example. Suppose the receiver is receiving 0, 1, 0, 0, 0, 1 instead of receiving the bit 0, 1, 1, 0, 0, 1, 1. So this is the actually data which is being transmitted from a transmitter to receiver. But at the receiver end, if he has received 0, 1, 0, 0, 0, 1, so we need to find out which position bit is errored. So to find out the which position bit, again we have a method like P1, P2, P4. Take the values of the same. What is P1 value now? Here to find the detecting the error, same. What are the positions for P1? It is 1, 3, 5, 7. So take this example same. I'm writing here 0, 1, 0, 0, 0, 1. Write the positions. This is P1, this is P2, and this is D1, P4, D2, D3, D4. That is first position, second position, third position, fourth, fifth, sixth, and seventh position for the data what they have received it. Now what is the value in the first position? It is 1. In the third position, because P1 value is 1, 3, 5, 7. So in the third position we have 0. And in the fifth position also we have 0. In the seventh position is 0. We transmitted it with even parity, isn't it? But the number of ones here it is odd number. So to make it even, P1 value should be what? It should be 1. Repeating again, this is the transmitted data frame what receiver has received it. Now this is the frame of 7 bits. from which we need to find out which bit has been detected an error. So to find that, we have to go with the frames. So the same framework 0, 1, 000, 11. What is the positions? First position, second position, third, fourth, fifth, sixth, 7 bits. And in the first position, it represents P1, P2, D1, P4, D2, D3, D4. What is P1 value? As in the previous slide, we have shown you that the P1 value is calculated by the positions first position, third position, fifth position, seventh position in the frame. So first position it is 1, 1. In the third position it is 0. In the fifth position it is 0. And in the seventh position it is again 0. Now count the number of ones. We have transmitted the data bits in even parity. So for even parity, the number of bits should be even. So but here we have odd number of ones. So that's the reason P1 is equals to 1. It should be P1 equals to 1. Similar way for P2. What is the formula? Or what is the position for P2? It's 2, 3, 6, 7. Now find the values in that particular positions. What are they? In the second position, we have 1. In the third position, we have 0. Sixth position, 1. Seventh position, we have again 0. Now check it. How many number of ones are there? They are even number. So the data transmitted is in even number. So what should be the P2 value now? 0. P2 value should be 0. P1 value should be 1. Now similarly, find out for P4. What is for method for that? The positions are 4, 5, 6, 7. Should we go for next number? No, because it's of 8 bits frame. So the maximum number is 7. Then write down the position values. In the fourth position, we have 0. In the fifth position, we have 0. In the sixth position, we have 1. Seventh position is 0. Come to here. How many number of ones are there? It's only one number. It's an odd number. So to make it even, P4 value should be 1. Therefore, what are the position values? P4, P2, P1. P1 value is 1, P2 value is 0, and P4 value is 1. This is what is given in the binary. This is your P1, P2, and P4. Now, binary equivalent value in the decimal it is power of 2. 1, 0, 1. 2 power 0, 2 power 1, 2 power 2. What is the value here? For 2 power 0 it is 1 plus, for 2 power 1, 2 into 0, 0 plus 2 power 2 is 4. 4 into 1 is 4. So the value is 5. So that is decimal value is 5. So this binary equivalent is equal to 5. This is the position which is getting error in the transmitted data. So therefore the error bit is at 5th position. Now we have identified, we have framed the data frame, we have transmitted, and we have identified the error in the 5th position. Now how to correct it? Now that is this. How to correct the bit? The received data is what now? Same 0, 1, 000, 11. In this we identified that 5th position has to be changed. So swap that 5th position. Already we detected that 5th position is in error. So in correcting method, that particular position bit has to be swapped. If it is 1, change it to 0, and if it is 0, change it to 1. So the position is 5th, flip the 5th bit. That is this. First position, second position, third, fourth, 5th position. So this bit has to be changed. Here we have 0. That 0 has to be flipped to 1. Then your correct data bits will be 0, 11, 00, 11. This is the data what a receiver has to receive it, and we have changed the 5th position to from 0 to 1, and this is the actual data. Now from this, what is the data that has been transmitted from the transmitter to receiver? Because this frame is with parity bits plus even the data bit. Now I have to recover the data bit. How do you recover? Same again, by going with the framing, that is your data frame positions. So this is your P1, P2, data 1 D1, this is for P4, this is for D2, D3, and this is for D4. And what are the data positions are? D4, D3, D2, D1. Write down. For D1 it is 0, for D2 it is 1, for D3 it is again 1, and for D4 it is 0. So the data what actually transmitted from the transmitter to receiver is 0, 1, 1, 0. Here the position, third position, 5th position, 6th position, and 7th position. And the data completely and the transmitted from the transmitter to receiver along with the parity bits is 0, 110011. Clear, guys? So in this slide, what we have to find it, how to detect the error, how to correct the error. For detecting the error, we'll use the method of the P1, P2, P4, the parity bit positions. And if you are going with even parity, then we'll see the number of even numbers. If they are not equal to even number, then we'll add one. I mean, we'll make the one position. And if they are even number of ones, then we'll replace that parity bit with respect to 0. This is how we'll find for detecting the error. And for correcting, after detecting the position, that particular bit in the transmitted data, we'll swap it. If it is 1, we'll change it to 0, and if it is 0, we'll change it to 1. And write down the complete sequence frame. 0, 11, 00, 11 is the bit which a receiver has received correctly. From this, how to retrieve the data? Again, based on the positions. Write down the position values. Write down D4, D3, D2, D1 values. This is 0, 11. So this is the data and this is the frame what a sender has transmitted to the receiver. This is how we'll find the framing, we'll find the error, and we'll correct the error using Hamming code method. Now coming to the advantage. By using this Hamming code method, it's very simple implementations because we have used only the positions, and that is power of 2. We have not used any complication numbers, right? So that's the reason it's a simple implementation, and it corrects a single bit errors, and that's the reason it is very high reliability. Hardware complexity is very less, that's true, and it is used in error correcting code memory. All the memory devices like flip-flops or SRAMs and all this, if you are transmitting any data, then correcting of that with respect to single bit can be done easily by using this Hamming code method. The limitation is, as I said, it cannot correct multiple bit errors, and extra parity bits increase the redundancy because we are using P1, P2, P4. If it is of more number of bits, 8 bits, and for 8 bits, how many parity bits we are supposed to add? We should add again 4 parity bits. So it becomes P1, P2, P4, P8. So totally 8 plus 8 data bits. For example, suppose if you are transmitting a data bits of 8 bits, then for this, how many parity bits we are supposed to transmit? That is again based on the formula 2 power r greater than or equal to m plus r plus 1. So r value should be equals to 4. Then only this condition satisfies. It means that we need to transmit 4 parity bits. Now how many the frame bits will be there? Data bits plus parity bit. So that is equals to 8 data bits plus 4 parity bits equal to totally 12 bits of frame we are supposed to transmitted to the receiver. This is how the circuit, as the number of parity bits are getting increased, the frame gets increased, and that is this, the extra parity bit increase the redundancy and calculating it. It is less efficient for longer message because the more number of bits. So finding the error, if we get any multiple errors, then this cannot be used. That's the reason it is less efficient for longer messages. Hamming code is used for shorter messages for a single bit error correction and detections. I hope the video is clear and the content is also clear. Thank you.